Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem number of submatrices that sum to a given target. So given this matrix over here, what exactly is a submatrix? Well, their definition, of course, is going to be more complicated than it needs to be, but basically it's any rectangle inside of this matrix. So this is a square, but we could obviously also have this, we could have this, we could have this, any of them. So I guess the natural approach would be to get every single submatrix in here, compute the sum, whatever that happens to be. Let's say it's X, then check, is X equal to the target? If it is, then we should take our result, our count, and then add 1 to it. If it's not, then we don't do anything. So let's just give that a shot, because surely there's no better way to solve this problem than to get every single submatrix. Doing that is not super easy. It's not super crazy, but it's not like trivial. So how do we even think about a submatrix? Well, let's define it for us as a pair of two coordinates, because we know that the submatrix, like let's say this is 1, for example, it's going to have a top left corner and it's going to have a bottom right corner. So we need 4 pointers to actually define it. You could use X and Y, kind of like the problem does, but that can get kind of confusing because with matrices, X actually goes on this side and Y goes here, but a lot of people will do the opposite. So instead of confusing yourself, I prefer to use row and column. So I'm going to say row 1 is going to be here. That's the beginning row. Row 2 is here. Column 1 here and column 2 here. Those are our 4 pointers in this case. So in other words, for us to enumerate every single sub matrix in the original matrix, it looks like we need 4 for loops because we have 4 pointers. And that's actually not it. That just tells us like what each submatrix is. After that, we have to go through every value in the submatrix and accumulate that. And that's going to be another 2 for loops nested inside those. Now, the dimensions of this, let's say, are m by n, because it's not necessarily going to be a square matrix like this one. So we need 2 pointers for this, 2 pointers for this, and then this, like the inner 2 loops, that's also going to be like iterating over this entire thing, which means every single row, every single column. So therefore, it's going to be m cubed times n cubed. Doesn't look very efficient, and I actually won't even bother coding this one up. But the question is, given everything I just showed you, what part of this do you think would be the easiest to optimize? I mean, we kind of have to create, or at least look at every single submatrix. This part doesn't look easy to optimize if it's even possible. But this part, accumulating the sum of a particular submatrix, it might be possible to do that. Let's try to simplify the problem. If we had a one-dimensional array, do you know how we might be able to, like, let's say we just want to compute the sum of an arbitrary subarray, and it could be any possible subarray. Do you know a way we could possibly compute that in constant time? Well, at first it looks like there's not, because we kind of have to iterate over every element in here. But we have technology. We have the power of pre-processing our data. What we can do is compute something called prefix sums. And a prefix sum is pretty simple. It just means we take every single prefix starting at the beginning of the array. It's basically a subarray starting at the beginning of the array and compute the total. So this would be a prefix, and then we'd get both of these elements, add them together and store that here. So this is a prefix, same thing here. This would be a prefix, etc., etc. Now, if we do that, going back to the original problem, to compute the sum of this prefix, all we need is take the element here, which tells us the total of all of these elements, and remove from it the element here, which tells us the total of all of these elements. That logically looks like it would give us the total of this subarray, and that's what prefix sums do. Can we apply that in 3D somehow? Let's try. When we were talking about a one-dimensional array, we computed the prefix sum starting from the beginning of the array. Similarly, let's try to do that in this problem. We know that a submatrix might start anywhere. Like the top left corner could be anywhere. It could be here, could be here, could be here, anywhere. But to simplify it, let's say that our top left is always going to be here, and this is kind of the way we're going to do prefix sums. I don't know a good word for it, maybe submatrix sums. That's probably the phrase that I'll be using throughout this problem. I don't know if that's like the accurate way to say it. But submatrix sums starting from just this top left corner. So what would that mean? That would mean getting this, like so far we're just doing one dimension, right? The prefix here, and then also the prefix here. So that was one dimension, and going over to 2 dimensions would be like this. Now we're computing this, and I guess I'll actually just compute it in front of you. So the first row is gonna be 0 here, and then computing these 2. And the way we're gonna compute the value that goes here is just by taking the original value here, which is 1, and then adding to it the prefix sum that's over here. So that is gonna remain as 1 right now. And then to compute the value here, we take the prefix sum plus 0. We're gonna put a 1 here as well. To compute the value here, we take the original, and what do you think we should add to it? Because remember, the value that goes here should represent the sum of this, and that makes it obvious we want the value up above. So we take 1 plus 0, and then this stays 1. What about over here? And this is where things actually get interesting because, I haven't even told you why we're computing these in the first place. We don't necessarily know this is going to help us. So now let's actually think about this. Let's say we want the sum of this matrix right here. How do we get it? Well, let's suppose we've already computed the submatrix sums. Let's say, for example, this value over here represents the sum of all of these elements. Okay, how do we calculate this efficiently, perhaps in constant time? Well, we know that the value over here is going to tell us the entire sum of the input array. But we don't want that, do we? But luckily, the value stored over here tells us total of all the values over here. And luckily, the value over here tells us the total of all the values stored over here. So what can we do? Can we just take this value and subtract these 2 values? Well, it kind of looks like there's a problem over here, doesn't it? Because if we try to do that, we're going to end up subtracting this value twice. What does that mean? Does this approach not work? Think about it for a second. How could we fix that? Well, we're literally computing the submatrix sums. We have the value that's going to go here. Even if it wasn't just a single value, if this was a matrix, we would still have all of that portion. The duplicate portion is going to be stored over here. So what we can say here is for this particular matrix where R1 is here, R2 is here, column 1 is here, and column 2 is over there. So now we pretty much have shown that the submatrix sum of this particular matrix is equal to, and I'm actually gonna call this total, because let's say we've already computed the values from this submatrix sum. Then to remove this coordinate over here, we're simply gonna say submatrix sum. This is what I'm gonna call the 2D grid on the right, by the way. It's simply gonna be the row up above. That's row minus 1. So here we say row 1 minus 1 at column 2. So we subtract that. We also subtract the value over here on the left. So subsum at row 2 at column 1 minus 1. And I added a negative over here because we're subtracting these 2, but we're adding the value over here. So subsum at row 2, column 2. Sorry, I made it a little bit smaller. We're running out of space. So this is the portion over here. This will add the whole matrix. And these 2 will remove this part and this part. And lastly, we want to re-add the top left corner back. So here we say add subsum of row 1 minus 1 as well as column 1 minus 1. So this is the formula you're going to see me using in the code explanation. Just to clarify, the only thing that I've proven to you is if we can somehow compute the submatrix sums, then we can easily compute the sum of a submatrix in constant time. But how exactly do we compute these submatrix sums? So far, it's easy. So far, we got the first row. That was trivial. That's just prefix sums. And getting this value, all we had to do is just take the value up above because it's also kind of a one-dimensional array. But now we finally got to the 2D portion. And it's going to be pretty much the same as what I just showed you, because to get the value here, we're trying to compute these 4 values. So obviously we take the 1 over here and put 1 here. We take the value up above, which tells us all of these 2. So add 1 again. And we take the value to the left, which tells us these 2. And so we add the 1 again. But don't forget, we want to probably remove this top left because we just added it twice. Because we added this portion and then we added this portion. So that's all I'm saying here. To compute a value at a coordinate like this in this array, we're going to look up and look left, add those, and then we're going to subtract the top left. We're also going to add the original value here as well. So let's quickly compute this now. So in our case, we just do the 1 plus 1 plus 1. We get a 3 here. Now to get the value here, look up, look to the left, add the original value. That's going to be 3 plus 1 plus 1. That looks like 5 to me, but don't forget to remove top left. So we end up with a 4 here. And that 4 looks right to me because when you look at this array, it looks like the sum is 4. Okay, here, same thing. Look up, look to the left. But now we kind of realize we're probably going to need to handle the out of bound cases, which isn't going to be super hard, but just keep that in mind. Because if we're looking up, left, and top left, we might go out of bounds. Now, in this case, the original value here is 0. We add 1 to it, we get 1. Value to go here, the original value is 1. We look up here, so then we end up with a 5. Don't forget to remove this. So we end up here with a 4. The value here is 0. We add 8. Subtract 3, we end up with 5 here. Does that look right? 5? Yep, that looks like the sum of the entire matrix, so we did this correctly. Now that I've shown you all of this, we can code up the solution. If we can compute every submatrix in constant time, the number of submatrices is m squared n squared, so that's going to be the time complexity of this solution. And it looks like space complexity is going to be big O of m times n. Let's code it up, but at least in Python, this gets time limit exceeded. Okay, so with 2D grid problems, I like to get the dimensions because I like to refer to them as the number of rows and the number of columns. And the first thing we're going to do is compute that submatrix sum 2D grid. So first, I'm just going to create a 2D grid of the same dimensions up above and just fill it in with all zeros. And then I'm going to just traverse over the grid. So for row in rows, for column in columns. Now, to compute the value that goes here, submatrix sum at this coordinate, we know at the very least we're going to add, and I think we probably don't need parentheses, we're going to add the original value, so matrix at row column. Then we want to add the top value, then we want to add the left value, and then we want to subtract the top left value. Sorry if that sounded confusing the way I spoke it, but the way I'm going to set these variables up isn't going to be super crazy. So let's say the top is going to be equal to submatrix sum, and we know that's the one just up above, so it's going to be row minus 1 in the same column. But the problem is, which one of these could go out of bounds? Probably this one, row minus 1. We're subtracting from it. So let's only do this if row is greater than 0. But if it's not greater than 0, let's just say the top sum is 0. That's not a bad default value to put in this equation. It won't change anything. So we're going to do that. And for left, let's say it's equal to the submatrix sum in the same row, but from the column, we want column minus 1. But we're only going to do that if column is greater than 0. Otherwise, we'll set this to 0. And lastly, we want top left, and that's going to be submatrix sum at row minus 1 as well as column minus 1. So either of these could become negative. And we could say if row and column are greater than 0, but a slightly shortcut is just taking the minimum of both of those and checking if that's greater than 0. If the minimum is equal to 0, then we'll evaluate to false and then assign this to 0. So this is what we're doing. You don't have to do it this way. You could actually write out an if statement and then put code inside of it. This is just a good style, I think, because regardless, this formula now works. We don't have to like write this formula multiple times. To finally actually count the number of submatrices that satisfies the condition, we're going to count that in this variable and then we're going to return it. Now let's try to enumerate every single subarray. So we can do that like this for R1 in all of the rows and for R2 in all of the rows that come after the first row. So for R2 in range R1 all the way up until the number of rows. Well, I guess not just after, this could include this as well. So I kind of misspoke. And pretty much same thing with the columns. So for column 1 in range of columns, and then column 2 will go after that, column 1 up until the number of columns. A lot of loops. So now we have our submatrix and we want to compute the sum of it. We have the 4 pointers. So let's say the current sum is going to be equal to the subsum ending at R2, column 2, but we know this is actually too big. What do we want to do with this? We want to subtract from this the top, we want to subtract from this the left, and then we want to re-add the top left back because we subtracted it twice. So just like this. If you look, this is actually kind of the opposite of the above formula. But if this is confusing to you, I would just rewind back to the drawing or maybe draw it out yourself because it 100% does make sense when you actually look at a picture. Because remember, all of these submatrix sums always start at the top left corner, whereas these do not start at the top left corner. That's why we have 4 pointers here. Now let's just get these 3, top left and then top left. Said that twice. So top is going to be this. It's going to be the subsum at R1 minus 1 and staying at column 2. But again, we're only going to do that if R1 is greater than 0. Otherwise, let's set it to 0. Left is going to be the subsum at R2 and then column 1 minus 1. And only if column 1 is greater than 0. Otherwise, it's going to be 0. And then top left is the easy part, I guess. Subsum is going to be R1 minus 1 and then column 1 minus 1. And again, if minimum is greater than 0. So there we go. We got the current sum of this submatrix, but what do we do with it? Well, if it's exactly equal to the target, then let's increment this result. Whoops, had a typo. This should be subsum, but you see that this solution actually gets time limit exceeded. So let's see if we can optimize it. Okay, welcome to the 7th layer of hell where we're going to try to optimize this one. And I'll just tell you that it's going to be really hard without the background knowledge of Leetcode 560. So if you want to go watch that video, you can, but I'll try to review the important part right now. It's basically this same problem, except with one dimension. Suppose the question that we're actually trying to ask is how many subarrays in this array sum up to some particular total value, some target. Well, in an array, there are n squared subarrays, like n starting from the beginning, and then n starting from here, etc., etc. There's going to be a lot of subarrays. So for us to even get the sum of each particular subarray, even if we do it in constant time, we still have n squared subarrays. How can we possibly solve this problem more efficiently? Well, let's reframe the problem. There is some target value we're looking for. Let's say here, let's iterate over this array just a single time. And every time we land at a position like this one, let's ask how many subarrays ending at this position sum up to the target. So how many subarrays would that be? It'd be possibly this one, and possibly this one. How many of these guys sum up to the target? Well, how can we possibly make that more efficient? Don't we have to look at every single subarray? Think about the math for a second. Let's say the value at this position is cur. Let's say we also have something we're keeping track of called the current sum, which tells us the total of all the values that we've seen up until this point. Now, there's something really, really clever that we can do. We can have a hash map where for every single prefix sum, we keep track of how many times we've seen prefix sum with that particular sum. So just assume that we have this. Assume that we have, up until this point, we've computed every prefix sum, this prefix sum, and this prefix sum. Now we're going to take a shortcut. We're going to compute the current sum minus the target value that we're looking for. Current sum minus target. What does that tell us? It gives us, let's say, a value that I'm going to call the diff. At first, you might think I got this equation wrong. At first, you might think, shouldn't we take the target and subtract from it the current sum? No, because what the diff represents is this is the value that we need to remove from the current sum to make the current sum equal to the target. So if I were to write out that equation, just to prove the algebra to you, I'm saying current sum minus the diff is equal to the target. And if we rearrange this and solve for the diff, we're going to get diff equals current sum minus target. So that's the diff we're looking for. What do we remove from the current sum to make it equal to the target? And the reason for that is because if we happen to have a 500 IQ and we were able to come up with the idea that we should count the prefix sums like this, then by the time we get here, we know, do we have any prefix sums that we can remove such that this subarray is equal to the target? And not only do we know how many prefix sums we have. Let's say it's somehow possible that removing that prefix sum makes this equal to the target. Let's say it's also possible that removing this prefix sum makes it equal to the target. And that would probably only be the case if both of these are 0. And maybe this value here is like 5 and the target is also 5. But that's the idea. We're doing this in one calculation. We are computing all of the subarrays ending at this position such that it's equal to the target. That's not simple to understand. It's even harder to come up with, but that's the idea that we use with one dimension. We optimize n squared down to big O of n. So can we do the same thing with this? And the answer is yes. Let me show you how. Oh, and by the way, when we initialize that prefix sum count, that like hash map, we're always going to initialize it mapping the key 0 to 1. And the reason is because that's kind of like a base case. Let me quickly show you an example of why we would do that. Suppose target is equal to 5. Suppose this array, the first value is equal to 5. So now 5 is equal to our current sum. We take current sum minus the target, which gives us a diff of 0. So now to our result, we want to add how many prefix sums have we seen so far with a diff of 0. If our hash map is empty, we're not going to end up adding anything to the result. It's always going to stay 0. That's why we initialize it, like I said. And also, as we are iterating through this array, every time we compute a current sum, at the end of that iteration, we're going to add that current sum as a prefix sum to the hash map I was talking about. Now let's jump in to this. When we had a single array, instead of us looking at every single possible subarray, which would need 2 nested for loops, and also 2 pointers, right? One left pointer and one right pointer to tell us the boundaries of the array. We actually just used 1 pointer when we were talking about the optimization right now. And that optimization told us the ending of the subarray. Similarly, we're going to do the same thing in 2 dimensions. We're still going to have 2 pointers for row 1 and row 2. I'm actually going to put them here for the example I'm going to show you. But we're going to have just a single pointer for the column. And that's going to tell us where that submatrix ends. Suppose we're doing that here. So when we start, we're going to initialize a hash map, and this hash map is going to map prefix sums to their respective counts. In this case, it's more of like a prefix submatrix or whatever you want to call it at this point, but you get the idea. So right now we're over here, and we're actually going to be mainly iterating over this matrix. So I'll actually be mostly on this side. So we want to know right now the current sum. The current sum tells us this. How do we get this? Well, we know that the value over here tells us this entire thing, but we want just this. So what we're going to do is take this value and remove from it that value. So right now, our current sum is going to be equal to 1. It's going to be just this. And by the way, I didn't show it, sorry. The hash map will be initialized with 0 mapped to 1 so far, at least. Now, to compute the diff, I'm going to take current sum and subtract from it the target. Let's say that the target is equal to 0. So current sum minus the target is going to be 1. We check, is 1 in the hash map? No, it's not. So we're done with this. This submatrix does not sum up to the target, or well, this submatrix, sorry. These are the sums. This is the original submatrix. So it doesn't sum up to the target. Now let's move on. Before we move on though, we do take that sum, which was 1, and then map it to the count, which is now going to be 1 as well. Next, we're over here. Our column pointer is going to be shifted over here. We want to know at this point, you might be thinking we're only going to be looking at this submatrix. It's true, we're looking at this submatrix, but we also want to potentially consider this submatrix at the exact same time. In other words, we want to know, given that these two rows are fixed, how many submatrices ending at this column, which like I said, is just either this or this, which one of those sums up to the target? And we can do that in constant time. First, we compute the current sum. We do that by taking, once again, this bottom value and subtracting this value, because this value tells us this thing, and this value tells us this thing. So we get 4 minus 1. That's going to be equal to 3. Current sum is 3. And that looks accurate to me when you look at the original matrix. There are 3 values there. Once again, we would take current sum minus the target, which remember the target was equal to 0. And we would ask ourselves, okay, that is the sum that we need to subtract from here to make a submatrix that is equal to the target. Now, in this case, that doesn't exist. Current sum, which is 3 minus 0 is 3, and 3 does not exist in the hash map. But let's just change the example just for a moment. Let's assume target is actually equal to 2. So then the number that we're looking for is 3 minus 2, which is 1. We want to know, is there possibly a prefix, and so far this is the only prefix we've inserted, is there a prefix that sums up to 1? How do we know that? Well, we would have inserted it in the hash map. It looks like the key 1 does exist in the hash map, and the count is equal to 1. So this count is what we're going to add to the result. So that submatrix here, this is that submatrix that sums up to 1. This is the current submatrix that we're at, which sums up to 3. If we remove this guy, then we end up with a sum of 2. And if 2 happens to be our target, then we found what we're looking for. This is the idea that we are going to follow. I'm not going to continue drawing this out because I don't think you want to be here all day. And notice if we make this optimization, which again is not easy to come up with, we cut down the number of pointers from 4 pointers to 3 pointers. And therefore the time complexity is going to be m squared, which let's say is the number of rows, times n, which is the number of columns. That's the big time complexity. The space complexity didn't change. So let's code this up now. Okay, so I'm actually just going to take all this code here and remove it, and then just have the column here going through all the columns. And every time we get to a new pair of rows, these are going to be fixed, and that's when we're going to start counting for our hash map. I'm going to create the hash map. I'm going to call it count. Initially, it's just going to be a hash map. A default key is just going to be mapped to 0. So this will tell us for every prefix sum or submatrix sum, whatever you want to call it, is going to map to some count. And we're going to initialize it such that 0 maps to 1. Now for the first step, which is just computing the current sum of the submatrix defined by these pointers ending at this column. That's going to be current sum is equal to the submatrix sum ending at row 2 and the current column that we have, subtracted by the submatrix sum at row 1 minus 1. Remember the row that's up above at the same column. And this could go negative. So let's wrap this in an if statement so we can say this. If row 1 is greater than 0, that's when we do that. Otherwise, we set this to 0. Okay, great. Now we compute the diff that we're looking for. And remember, it's kind of backwards. You'd expect it to be target minus current. That's how 2sum works. This problem is kind of the opposite of 2sum. So we're actually taking current sum and subtracting the target. And so this diff is what we're looking for in our hash map. If we find it in our hash map, then we want to add this to the result. If we don't find it, the default value with a default dict is just going to be 0. So what we can say is result, add to this whatever we find here. Either it exists and count is non-zero, or it's equal to 0. And the last step of this, don't forget, we want to actually be updating this count as we go, as we compute every current sum. We want to update the count so we can say count for this current sum, or a prefix sum, whatever you want to call it, is now incremented by 1. Oh my lord, this is not an easy problem. This might be one of the hardest I've done in a while. I'm gonna run the code and it looks like it works and it's about as efficient as you can get. If you struggled with this problem, please don't feel bad. Consider checking out Leetcode.io. There's a lot of resources on there that I think can help you. If you found this helpful, please like and subscribe, and I'll see you soon.